Hello everybody, welcome to my channel. My name is Ange, and in this video we're going to find out the value of negative 1/2 factorial. Good. So suppose we have a non-negative integer n, then n factorial like that is the same thing as n times n minus 1 times n minus 2 and so on and so forth. Okay, good, up to we have 3 times 2 times 1. Good. Okay, so this factorial makes sense when the input is a non-negative integer. That is to say 0 factorial is 1. Good. When we say non-negative integer, that means we start from 0 and we talk about only integers. Okay, that's nice. But then how does that make sense to say negative 1/2 factorial, given that 1/2 itself is not a whole number, it's not an integer, and negative doesn't make it positive, so it becomes a negative. How does it make sense, right, based on this definition? Well, that is a case where we generalize the factorial notation, okay, to involve numbers like this. Good. And the generalization is what we call the gamma function. So the gamma function is like the continuous case where the gamma factorial is for the discrete case. By discrete we mean it's only for countable okay, a countable let's say set. Good. Where we have integers that you can count, something like that, while gamma function is for real numbers. And the real numbers have a pattern, and we're going to talk about it right now. Well, first of all, the notation for gamma function is this, where this right here, this dot is the space for the input. Good. But what kind of input? Well, this is the kind of input that gamma function can be defined on. So let's say alpha be a real number, right? Be a non-zero real number, okay, and it is not a negative integer. Okay, let me put it this way. Be a non-negative integer. That means let's have a non-zero real number which is not a negative integer. In other words, suppose we have a real number that is not a negative integer and it's not 0, then the gamma function can be defined on such a real number. So when we define the gamma function on such a real number, this is the definition of the gamma function. Is going to give us the integral from 0 to infinity, okay, of e raised to the power of negative t, good, times t raised to the power of, well, this input here, which is alpha, we're going to subtract 1 from it, and then we're going to put the dt right here, where this t here is a dummy variable. In other words, I can change t to x to y to u, whatever I want. Okay, so this is the definition of the gamma function, and this is what we can use. Okay, so this is where this one makes sense. But as a generalization of the factorial, shouldn't it have some relationship with factorial? Of course it does. This is it. So this gamma of alpha right here is the same thing as alpha minus 1 factorial. In other words, if you put in 2, let's say gamma of 2, so gamma of 2 is going to be the same thing as 2 minus 1 factorial, which is 1 factorial, and we know that 1 factorial is 1. Gamma of 3 will be 3 minus 1, which is 2 factorial, which is 2. Gamma of 4 is 3 factorial, which is 6, and so on and so forth. Right? Good. Okay, but this notation also lets us know that since we subtract 1 from the input, in other words, the input for the gamma function will become 1 more than the input of the factorial function. It means that if the gamma function is, let's say, alpha plus 1, the factorial will be if we have gamma of alpha plus 1, we're going to have alpha factorial. In other words, we reduce the input by 1. So that's the essence. Okay, so let's see how this negative 1/2 can come in. Okay, using the gamma function. Okay, well, from this definition, it means that this right here is alpha minus 1 factorial. So given this, we can use that to define it. So let's come over here. Good. So we write out what we want, negative 1/2 factorial, which is the same thing as gamma of, remember, for the input of the gamma function, you increase it by 1. So you're going to add 1 to 1/2. That gives us, add 1 to negative 1/2. That will just give us 1/2. That is the same thing as that. And using the definition, gamma of 1/2 will be, so the definition of the gamma function is that the gamma function, let's say gamma of alpha, where alpha is nice, by that alpha satisfies the definition, is the integral from 0 to infinity. So it's what I've written before. Then so this is going to be the same thing as the integral from 0 to infinity of, well, that will be e raised to the power of negative t times t raised to the power of, so this input here is 1/2. So we're going to subtract 1 from 1/2. That just gives us negative 1/2, which we started with. All right. Okay, so we put the dt right here. Well, that is just so because I showed you that this right here is the same thing as that. Anyway, now from this, how can we evaluate this integral? So the result here after evaluating this integral will give us will give us what we're looking for, which is gamma of 1/2, which is negative 1/2 factorial, based on the relationship. All right, good. So how do we evaluate this integral? Well, I'm going to start off with a substitution. I'm going to say well, I notice this is t raised to the power of negative 1/2, just like saying square root of t at the bottom. So I'm going to need some square to cancel out with the square root. So I'm going to let u squared be t. Good. Well, we're going to differentiate that to get the dt. So we differentiate this both sides with respect to t. So that'll be 2u du. Is differentiating t with respect to c, we get 1. So the dt comes over here. Okay, treating it like a fraction. Good. Okay, so that means this integral will become, which is this, is the integral. So the bounds of integrations will change, or may change rather. Now, when t is 0, u squared will be 0. And that means u is 0 when t is 0. Okay, then when t approaches infinity, square root of infinity also approaches infinity. That is, square root of a variable that is approaching infinity also approaches infinity. Okay, so this is e raised to the power of negative of. So we've replaced t with u squared. So in place of t, I'm going to put u squared. Okay, that's nice. Then in place of t again, this is t. So that will be u squared. Okay, maybe let me just show you what I mean. So this is u squared, but t has been raised to 1/2. So the square from the u will be cancelled with the 1/2 power from the t. Okay, leaving us with negative 1. So we put the negative 1 down right like that, and then the dt, well, dt will be replaced with 2u du. Good. So this is what we're going to get. This will become, well, we're going to pull out this constant multiple. That's a factor. That's constant factor. Then notice that u and u to the power of negative 1/2 will cancel each other out. We'll be left with this du. Okay. Well, can you recognize this integral? This right here is the Gaussian integral, 2 times the integral from 0 to infinity. This is the Gaussian integral. It tells us that the integral from minus infinity to infinity of e to the power of negative, let's use u for that, u squared du. It has a value, and the value, I'm not going to expose it anyway, but of course, if you know the Gaussian integral, it's okay. And we're not going to use this approach, rather we're going to find things out on our own, okay? Probably the same method, but of course, we're going to learn. Good. But we may ask, how are this and this are the same? Well, they're the same because this function right here is an even function. When you evaluate an even function over a symmetric interval, you can just take half of that interval and then double it. Good. Okay, because an even function is symmetric about the origin. Okay, so that makes sense. Sorry, it's symmetric about the y-axis. Sorry for that. Okay. Anyway, it is the odd function that is symmetric about the origin. So how do we evaluate this integral? Okay, so that's the ball game now. So I'm going to start off with this. So let's consider this integral. So suppose we have this integral, let's say 2 times the integral from 0 to infinity of e raised to the power of negative x squared dx multiplied by itself. Now, since these two integrals are the same and we are multiplying them, it's going to be like the square of one of them. Well, notice that for each of these integrals, comparing it with what we have, this thing right here, is exactly the same. They are exactly equal. Remember, for definite integrals, the variables are dummy variables. In other words, the value of the integral is independent on the variable you're making use of. Okay, so that means this and this are exactly the same. But since we are squaring this, well, the result after evaluating this product, when we take the square root of that result, we're going to get what we want. Okay, so yeah, so what we want here is the square root of this right here, is the square root of this product. So let me just show you. Okay, so I want to say that when we take the square root of this product, that will give us the integral which we want. Okay, based on the explanation. Good. So let's go ahead and evaluate this. Then we are done. We take the square root and we are done. Good. Okay, so maybe you keep this in mind. I'm going to write it in a new page. So what we want is, like I said, the integral from 0 to infinity. Then the next one is this. again, since the variable is a dummy variable, look at what I'm going to do. I'm going to rewrite it so that we change the variable from x to y is the same thing. This is e to the power of negative y squared. So I've changed that dy. Okay, so I'm going to put the dy like that. Good. Okay, so by a similar reason, so this is going to be, well, let's multiply these two. This is 2 times 2 is 4 times the integral, well, from 0 to infinity, that's the first integral, and the second integral, that is the integral from 0 to infinity. So these two functions, we can join them together this way. This is e raised to the power of negative x squared. Okay, we multiply that by e raised to the power of negative y squared dx dy. Okay, that's nice. So let's combine the two functions. E raised to the integral from that to that, integral from that to that. We combine these two functions since the bases are the same. So we will keep the factor of the negative one will be left with x squared plus y squared. Good, and then we put the dx dy like that. Of course, I hope you can see what I'm trying to do here. Polar coordinates, right? So I'm going to make I'm going to try to convert this from the Cartesian coordinates to polar coordinates, and that will be by saying let x be r cosine theta. Okay, that will give us the x-axis, that is the value of x on the x-axis. Then y is r sine theta. Well, from these two equations, technically we square each of these equations and add them together. That will become x squared plus y squared. That will give us r squared, since the square of cosine plus the square of sine is equal to 1, so it will leave us with r squared. Okay, and then lastly, the derivatives, that is the product of the derivatives, the product of the differentials, the x times the y is the same thing as r d theta. Well, when we learn double integrals, okay, we can derive this right here, okay, using that the annulus on the polar plane. So let's visualize the Cartesian plane a little bit and see how we're going to relate it with the polar plane. So you given on a Cartesian plane, where this is the y-axis and this right here is the x-axis. Okay, so what this integral is, x value changes from 0 to infinity, so it's over here. The y value, that is this second integral, changes from 0 to infinity. In other words, we're looking at this first quadrant. Okay, on the first quadrant, the angle goes from 0 to pi over 2. So the angle over there is from 0 to pi over 2 on the first quadrant. Meanwhile, the radius, which is r, is allowed to go from 0 to infinity because the value of x extends from 0 to infinity, same thing as the value of y. So maybe let me put it out here that the radius, let's make it to be positive, okay, so that we have some seeable annular domain. Okay, so from 0 to infinity, while the angle theta is from 0 to pi over 2. Sorry, let me put it out like that. Okay, so with that, this is what we're going to continue with. So this is what we're going to do. We're going to use that to rewrite the integral, that is the product, that will become 4 times the integral. So I'm going to keep these two integrals. I'm going to come back to each of them. Then we have e raised to the power of negative of, now notice that x squared plus y squared from this equation is the same thing as r squared. And then we have the x, the y, which will be replaced with r d theta. Good. So for the bounds of integrations, this outside integral is for the y. Now from 0 to infinity, so this outside is for theta, but theta changes from 0 to pi over 2. Then the inside integral is for r, which changes from 0 to infinity. Okay, as ranges from that to that. Okay, so this is going to be, well, I'm going to peel off one of the two, that is 2 times 2. So I'm going to write 4 as 2 times 2, but the second 2 will come into the integral. That means we're going to have the integral from 0 to pi over 2 times the integral from 0 to infinity. So when I bring the 2 in here, join it with this r, that becomes 2r e to the power of negative r squared, okay, dr d theta. Good. Here we can make a substitution. Let me show you the way they work. I'll say maybe let's make use of w. Let w be r squared. Good. So from there we can differentiate that. The w will become, well, that will be 2r dr. So notice what we have, 2r dr. That is the w. All right. from the derivative. So this is w squared, sorry, this is w. So when we do the substitution, we notice this is e raised to the power of negative w, then the w, and then we will integrate such an exponential function. You know, the result is going to be negative e raised to the power of negative w. Okay, so you do the derivative, and the integration, and then you see that's what you're going to have. So you're going to have to evaluate e raised to the power of negative w from the 0 to infinity, and then we put the theta over here. Okay, so we evaluate this right here based on the bounds of integrations. That means we're going to have the negative 0 from, sorry, this is negative 2, yeah, that will be from 0 to pi over 2. We substitute, we look at when w approaches infinity, e raised to the power of negative w will be breaking down to 0. As we approach infinity, that is e raised to the power of negative w as w approaches infinity. Then when w is approaching 0 from the right, this right here will be approaching 1. And like that's what we write down. So we subtract, okay? Then this is d theta. Well, this is negative 1, which will change the sign of this 2 out here to become positive 2, become the integral from 0 to pi over 2, then d theta right there. Of course, this right here is just easily, this is 2 times pi over 2, right? Which is just equal to pi. Okay, so that's the value of the product, is pi. So let's get back to what we started with. Remember what we said, that the result will be the square root of whatever we have. So since what we have there is pi, we take the square root of pi, and this right here is the value of a gamma of 1/2, which is the same thing as negative 1 over 2 factorial. So we can say that this right here comfortably is square root of pi. And that is what the Gaussian integral tells us. Oh, I think I cleaned it a little bit. Okay, anyway, it was a really long one. I hope you enjoyed the video. That's how to find the value of negative 1/2 factorial as square root of pi. Well, we can use this result to get some other interesting number. For example, 1 over 2 factorial. So this is not an integer, but it's a positive real number. So this is going to be the same thing as gamma of course, add 1 to this, right? That will be 3/2. Well, there is a relationship, or there is a property of gamma function that tells us that when we have gamma of some alpha plus 1, we can rewrite this as alpha times gamma of alpha. We can prove this easily using the definition of the gamma function, this integral right here. In other words, I'm going to rewrite this as gamma of 1/2 can be written as, 3/2 can be written as 1/2 plus 1. Which means from this right here, we're going to have 1/2 outside times gamma of 1/2 inside. But we know what gamma of 1/2 is. It is just square root of pi. Okay, so from there, this is going to be, well, 1 over 2 times that, which just gives us square root of pi over 2. So that is gamma of 3/2, which is 1 over 2 factorial, is square root of pi over 2. Meanwhile, negative 1/2 factorial is square root of pi. Okay, is that to also generate some other interesting numbers or results, and they use it to trick your friends. Anyway, okay, thanks for watching. Hope you like the video. Please don't forget to share the video with your friends, subscribe to my channel, and I'll continue from my next video.